All right, we're looking at the last two problems, 5 and 6, from the Taylor series FRQ Worksheet 1 AP Review. So number 5 says consider the series where p is greater than or equal to 0. Show that the series converge for p greater than 1. So when p is greater than 1, such as n squared, for instance, we know this series will converge because if we think about p-series test and direct comparison, we know that 1 over n to the p, where p is greater than 1, we know that must converge. And if that's the case, then 1 over n to the p natural log of n, that means this expression must be greater than 1 over n to the p. However, because it's in the denominator, the relationship is flipped around where we know this must be less than 1 over n to the p. And this fulfills the condition for comparison test, where if we know that a series is a known series is converging, then anything less than that converging series must also converge as well. So we can say that 1 over n to the p natural log of n converges by comparison test, direct comparison test. Part B, determine whether the series will converge or diverge for p equal to 1. So when p is equal to 1, we get 1 over n natural log of n. And this is something that we may have to use integral test for. So if we set up using integral test, I'm going to convert the n to be x's. So the integral from 2 to infinity for 1 over x ln of x. If we go through u substitution, we can let the u value be natural log of x. Derivative du over dx is 1 over x. dx equals x du. X du gets replaces dx. The x's cancel out. We're left with 1 over u. Limit as b approaches infinity. For the antiderivative is natural log of u, and then u value is ln of x, and then we evaluate the bounds. This is going to be an improper integral since one of the bounds is at infinity, so we'll let b hold that value. So plug in the upper bound first. So natural log of b minus natural log of 2. Natural log of b is going to be infinity. Infinity minus minus a constant or a real number is still going to be infinity. So we know the series must diverge. Since the limit does not converge, or the area doesn't converge, the integral doesn't converge, then we know the series must also diverge by the integral test. Okay, for C, show that the series will diverge for p between 0 and 1. So for p between 0 and 1, we can show that by comparison test that 1 over n to the p is going to be greater than 1 over n ln of n, right? And if that's the case, then we know that because we just shown from part B that this series diverge, we know anything greater must also diverge. So any p-value that's between 0 and 1 will cause this to be smaller, and this is smaller, then that will cause this fraction to be larger, and this is a larger fraction than this, then we know that the relationship is correct for direct comparison test. Since we know a known series is diverges, then we know anything greater than that known series must also diverge. Okay, last problem here, number 6 in the worksheet. Okay, let f be the function given by e to the x over 2. Write the first 4 non-zero terms and the general term for the Taylor series expansion. So we can build the e to the x over 2 starting with what we know. We know what e to the x is, which is 1 plus x squared over 2 plus x cubed over 3 factorial plus dot 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 plus x to the n over n factorial. That's our general rule. So if we want to build e to the x over 2, I can just replace every x in the polynomial with x over 2. So 1 plus x over 2 plus x squared over 2 squared times 2, x cubed over 2 cubed times 3 factorial. And we can also replace the x in the general rule with x over 2, quantity to the n over n factorial, which cleans up to be x squared over 2 to the n times n factorial. Okay, so don't forget, right, we have the general term that we also wrote out right here. Use the result from, so part B says use the result from part A to write the first 3 non-zero terms in the general term for g of x equals e to the x over 2 minus 1 over x. So the problem is helping us build these pieces together. So we have the first few terms of e to the x over 2. So I'm going to replace the e to the x over 2 with the first few terms of the Taylor polynomial. So all these terms minus 1 over x. Okay. The ones will cancel out. So if I divide each of these terms by x, I'm left with 1/2 plus x over 2 squared, 2 factorial, okay, so on and so forth. And then I can also build my general term, which is x to the n minus 1 over 2 to the n times n factorial. Okay. Okay, so don't forget, again, we need the general term. For the function g in part b, find g prime of 2 and use it to show that the summation of n over 4 n plus 1 factorial is equal to 1/4. So for part c, we're going to find g prime of x. So to find g prime of x, we're simply going to go through power rule to find the derivatives of each of these terms. So 1/2 goes to 0. This term becomes a constant, 1 over 2 squared times 2 factorial. This becomes 2x over 2 cubed through factorial. And then if we go through power rule, that's just basically n times x to the n minus 1 times 2 to the n plus 1 over n plus 1 factorial, right? Each of the, once we go through the derivatives, each of these terms will get affected as well. All right, so then to evaluate the derivative at 2, it'll be 1 over 2 squared times 2 factorial. And just replace every x we see with 2's. Okay. And now we want to show that the summation from 1 to infinity of n over 4 n plus 1 factorial is equal to 1/4. So what we can do is we see these few terms here, right? These few terms is essentially, if we clean this up, is the result of n over 4 n plus 1 factorial. Okay. So what that means is I can find g prime of x. Okay. So I can so we know g of x is e to the 1/2 x minus 1 over x, and if I just find the derivative of this expression and plug in 2, then that I should be able to get down to a value that will match up with what they want us to show. So if we go through the derivative rule here, we can go through quotient rule. So f prime g minus fg prime all over g squared. Okay, so f prime g minus fg prime all over g squared. Replace each of the x's with 2's. And once we do that, we get e plus 1 over 4, which the e cancels out. We're left with 1/4. And now we've shown that g prime of 2 is equal to 1/4.